So in this video, we're going to use calculus to determine intervals over which a function is increasing or decreasing, and we're going to do it in the case where the derivative is everywhere defined. So the example says, find the open intervals on which f of x equals x to the fourth minus 2x squared is increasing or decreasing. And so I put the graph of f of x here just as a useful tool for understanding what's going on. Again, when you use calculus to determine intervals over which a function is increasing or decreasing, we don't need to actually see the function, but having a picture of the graph of the function helps us to know if we've made a mistake or not. So intervals over which we're increasing or decreasing. So as per the previous video, the critical numbers are going to be used to establish open intervals over which we test for increasing, decreasing functions. So we want to look at this and say, where are the critical numbers? Well, here's the derivative of 0, here's the derivative of 0, here's the derivative of 0. So it looks like those happen at x equals -1, x equals 0, and x equals 1. So again, we don't need to see the graph to know this. We're going to use calculus to do it. But this gives us an answer key. By having the graph, we have an answer key. So step 1, find the critical numbers. So you take your function, you then find the derivative of the function, which is going to be 4x cubed minus 4x, which in factored form would be 4x times x squared minus 1. So first find your derivative, and the critical numbers in this case, because I can see by looking at the graph the function's everywhere defined. The derivatives are going to be everywhere defined. There's no cusp or anything funky going on. In fact, the derivative's a polynomial. So the derivative, we know because it's a polynomial, is defined everywhere. So the critical numbers are just going to occur when the derivative is equal to 0. And that's why I put it into factored form, because when we set factored form equal to 0, we just use the zero product property to break this apart as either 4x is equal to 0 or x squared minus 1 is equal to 0, and then we solve for x. So here x is equal to 0. There's a critical number corresponding to this point on the graph here. And then x squared equals 1. We take the square root of both sides, but when we do that, we get plus or minus the square root, and the square root of 1 is just 1. So our critical numbers are going to be 0 and plus or minus 1. So I'm going to go in here. I have a tool for organizing the information that I need to determine the intervals over which my function's increasing or decreasing. So I'm going to list my critical numbers in order, in ascending order. So the first one is -1. I'm going to put it right here. I'm going to put the 0 right here, which is my next critical number. And then my final critical number is x equal to 1. And then once you find the critical numbers, you establish open intervals using the critical numbers. So we want to recognize that as we're moving from left to right on the x-axis, we're coming from -infinity up to -1, the first critical number. So we're coming from -infinity up to -1. And then we move between -1 and 0, the next two critical numbers. So that creates the next open interval. We go from -1 to 0. And then we go from 0 to 1 between the next two critical numbers. And then once we get past the critical number of 1, the function f of x goes off to infinity. So the last open interval over which we're interested is the interval from 1 to infinity. And you can see graphically that each of these are going to correspond to the function either increasing or decreasing. Decreasing, increasing, decreasing, increasing over 4 distinct open intervals. So the three critical numbers generated 4 open intervals, and what I did was put the critical numbers on the boundary line between the intervals. So remember, if we're using calculus to test whether a function is increasing or decreasing, and I can see that on the interval from negative infinity to negative 1, as I move from negative infinity towards negative 1, I can see that I expect to discover that the function's decreasing. But when we use calculus, we don't need to see the graph. What we need to know is what is the sign of the derivative. Is the derivative negative? If the derivative's negative, the rate of change of the function is negative, which means the function will be decreasing in output values. If the derivative's positive, the function will be increasing in value because the rate of change will be positive. So what we need is a test value to plug into the derivative. So we need any number on the interval from negative infinity to negative 1 that we can then plug into the derivative and see if that test number gives us a positive or negative output. So in this case, what I want to notice is that if I pick x equal to negative 2 is in the interval from negative infinity to negative 1, and I can then take and plug negative 2 into the derivative right here. Here's my derivative. So let's just plug negative 2 into the derivative. So f prime, the derivative at negative 2, what's that going to equal? Well, it's going to be 4 times x, but x is negative 2, times square negative 2, and then subtract 1. So we're going to get negative 8 times negative 2 minus 1 is negative 3. So we get negative 24. So I can see that in my test number inside the interval, my derivative is negative. So the sign of the derivative in this interval, open interval, is going to be negative. And if the derivative is negative, then the function f of x is decreasing. And again, the derivative being negative just means that if we have a slope of a tangent line on that interval, the tangent line slope will be negative. So I conclude, because the derivative is negative in this open interval, I conclude that the function f of x is a decreasing function over that interval. And then I just step to the next interval from negative 1 to 0. I see that the function is increasing, but we want to use calculus to verify that the function's increasing. So I look at the open interval from negative 1 to 0. I pick a test value in that interval, so the number negative 1/2 is in the interval from negative 1 to 0. Plug negative 1/2 into the derivative, so calculate f prime of negative 1/2, which is going to equal 4 times negative 1/2 times negative 1/2 squared minus 1, and do the calculation. We get a negative 2 here. Negative 1/2 is a quarter minus the 1, and 1/4 minus 1 is negative 3/4, which simplifies to positive 3/2. So we see when we plug in the test number that we get a positive value for our derivative. So the sign of the derivative in this interval is going to be positive, which tells us our function is increasing on the interval from negative 1 to 0. And then we just step over to the next interval, the interval from 0 to 1. I can see visually that the function is decreasing, but the calculus check is going to be to pick a test value in the open interval. And it looks like x equal to 1/2 is in the open interval from 0 to 1. Plug 1/2 into our derivative, so evaluate the derivative at 1/2. So we're going to get 4 times 1/2 times 1/2 squared minus 1, just plugging the 1/2 into the derivative right here. Calculate the result. What am I going to get? I'm going to get 4 times 1/2 is 2, times 1/2 squared is a quarter. A quarter minus 1 is negative 3/4. So I get negative 3/2. So I see that my derivative is negative, which tells me my function is decreasing over the interval from 0 to 1. And then we just have one open interval left to test. Note that x equal to 2 is an element of the interval from 1 to infinity, so pop 2 into the derivative, so calculate f prime of 2. So it'll be 4 times 2 times 2 squared minus 1 is just going to be 8 times 3, which is positive 24. So the derivative is positive in this interval, which means on this interval from 1 to infinity, the function is going to be increasing in value. So we have an increasing function. So that's how you use calculus to establish intervals over which functions are increasing or decreasing.